Welcome back. We have, I sent out an announcement today. Did everyone receive it? So, I'm trying to clarify the last two exams. There's one at the end of the semester, at the last day of class, and then there's also the final exam. Are there any questions about the logistics of that, or subject matter, or worries, things of that nature that I didn't explain well enough?
Slightly related subject, I guess. Just curious, is there any opportunity for extra credit? I know it's close in the class, but...
So I don't like to assign. The reason I'm hesitating is I sometimes grade an answer 10 out of 10, and sometimes I'm known to give like 11 out of 10 if it's really out of the ballpark. In other words, it's you can get a perfect score, but then you can also truly impress me, in which case I tack on a couple of extra points. But it's a very whimsical thing. The other thing I'm hesitating about is I also have been known to, on a 30-point test, I've been known to put 4 problems on it, each worth 8 points. And so if you do the math, that's extra credit for, those are examples of extra credits that may or may not exist on the last 2 tests, depending on things. If your question was about extra credit was about, can I do something outside of class? My answer is pretty much no, because I feel that's a little bit unfair to the rest of the people. Right? If somebody comes up to me and says, oh, I need to do something else to get my grade up, I have to throw that out for the entire class, and then I'm changing the syllabus, and then so I have issues about equity, fairness and equity on those issues, and that's why I don't really do that.
Good at it.
No. I'm also trying to explain instead of just saying, I'm kind of explaining where I'm coming from as well. Okay, and sometimes fair is such a strange word, but my goal is to create a level playing field for every person that walks into class. Okay. So, anyway. All right. Oh, and then you'd also notice that on the final, I'm allowing for 1 page of notes, double-sided, your own handwriting, but you have to turn it in. Okay. And I'm going to, that suggests, in fact, that you have to turn something in. So even if your page of notes, even if you don't want to bring a page of notes, you should scribble Maxwell's equations down on it and turn that in and really impress me that was the sum total of your notes. Okay? All right. I was pondering about that too. What happens if I don't get a page of notes? Well, I'll probably include that. I'll probably have some algorithm for that. Okay. All right. Any other questions on that? On the homework test, 2 or 3 of those problems will be exactly from the books, from the homework problems, assigned homework problems.
One question on that. So I guess Bolanos and Slater are both in the homework. Is one book going to be on your homework? You have a Slater column, and then Bolanos are.
They're all assigned equally.
They're all assigned. Is there anyone that's specifically more focused? Or
no, they're all important problems. They're all important problems. Okay. Yeah, no, absolutely. In fact, when I shift over to the new textbook next year, the number of Slater and Frank problems goes up. So there's a lot of problems in there that are, but yeah. So they're both very important. In some respects, the Slater and Frank is such a cleaner book. It's then Bolanos is so cluttered, and sometimes confusing, and certainly confusing with the flow, that I give. So, yeah, but I'll just, what I do usually is scan the problems from the textbook and cut and paste them into the exam so that you see exactly what you've seen all along. Okay.
On the homework problems, they're like, is it going to be like a test where like if we need an equation, it'll be given to us, or are we expected to memorize? So you will have 1 page of notes. Oh no, I'm sorry. That's right. On the final day of class, you will not have a day of notes. Let me tell you a little bit where I'm coming from on that. You should not memorize
the answers to any of the questions on the homework. But if you really work the homework problems, there's like three kinds of students, at least three categories of students. There are students that don't believe in homework, and so they come in and they solve the problem. The first time they ever see it is on the test. They solve the problem there or not, depending on the luck of the draw on that day and what have you. There are students that do the homework by studying the solutions. They print out the solutions and they study them, and they keep their hands behind their back and they just study it. And if you're a mortal like I am, you don't usually do very well with that, because you haven't, you've seen the trick in front of you doesn't mean that you've sweated and come up with the trick. So and if that's the case, then absolutely you'll need a crutch, right? But if you've really worked the homework problems all semester, if you've really done them and worked with a study group or worked by yourself to really get it and really own those problems, it should be a really simple exercise. You'll be in there. You'll remember. You won't have memorized it, but you'll remember. You'll have muscle memory. You'll remember how the problems are supposed to go. And really what I'm testing for is whether or not you've done your homework in that manner. Okay, so I'm going to be fairly forgiving on sloppy math or minus signs, as long as I see that you've done this, that you own the problem and you have it in your experience base. Okay, so it's nothing to really be stressed about if you've done the homework. If you haven't done the homework, then I think I prescribe that for your Thanksgiving break. And that would be a really tough, to try to catch up with all of it by now. But, you might want to do that. So, because that's where it is. Invariably, I always end up asking the one question that you didn't get to or you didn't get to. Imagine I do that on purpose. I know exactly what homework you didn't do, and I ask it, but it's just random, right? Luck of the draw, Murphy's Law. So, okay. Any other questions? I want to be as transparent as possible. Okay, good. Now, last time so we've been talking about antennas, and the first set of antenna problems was the far field approximation, where we did a generic antenna. We were able to separate out the R part from the theta and the phi part. And so we covered, if the problem has to do with sending a lot of information a long distance, then we could break apart, we could treat we could treat antennas in terms of their shape factor, often called their gain, and then the propagation conditions from the Green's function. Last time, we changed gears a little bit and we did a complete problem, a complete solution to the most simple antenna we could think of. And this antenna was the dipole antenna. And the dipole antenna is actually it comes up a lot, because all we're asking for is that there's a current distribution that's much smaller than a wavelength. And if you think about a gigahertz is a foot. So anytime I have a little piece of wire that's the size of a paper clip or less, down to little metal iron filings, I've got a dipole antenna, right? Or if you think in terms of an optical wavelength, half a micron, well, you can fit a fair number of carbon bonds before you get close to that wavelength. And so most interactions of light with matter, has to do with dipole radiation. And then I started at a gigahertz, which is a moderately fast frequency, and I went up to 200 terahertz or 300 terahertz. But let's go the other direction. The wavelengths get longer and longer and longer. So if I'm at a 60 hertz, well, then everything's a dipole. Unless you're talking, city size issues. So for all those reasons, a dipole antenna is actually remarkably common. Now, it's not a very good antenna. That's one of the takeaways from what we're about to do, but it comes up a lot. So in the natural, stumbling around kind of a perspective, dipole interactions come up an awful lot. And it also gives us a chance to sort of look through all the mathematics of things. There's a lot of learning, I think, that goes on with the form of it. And let me review some of the highlights. I of course, I'm sitting at the front podium, so I get to make my life a little bit easier. I put my antenna right at the origin. No doubt, you'll have to shift it off center a little bit, and that's going to drive you crazy. Or no doubt, you'll have several off center, and that'll drive you crazy. And in fact, the antenna that we will start tonight will end up in that regime. Okay, so we'll have a little bit of a we'll look at that a little bit, and then moving even further from there, we'll look at offset dipoles, not in a general way, but in certain instances of symmetry. We wrote down the convolution integral. We were careful about what the J was in terms of that convolution integral. The nice thing about this J, the nice thing about being small, means that we can approximate the size of the size of the antenna with a delta function. And delta functions are very easy to work with when they're inside of an integral, because we use the sifting property. So this first and key integration for the dipole antenna was actually very, very easily done. Okay? And so we're left with an A. Okay? Now where things got a little bit tricky was the dipole's a line and the coordinate system is a sphere. And so I had to convert the A that points in the z direction to spherical coordinates. And so I had to do two-hole projections, two-hole dot products to get a cosine and a minus sine theta. Now, it turns out the next step is conceptually really easy. I have three components to H, but two of those are 0, just because of the phi symmetry. The way I've lined up the dipole relative to the z-axis, walking around it in the phi direction, the line looks exactly the same, whether I'm to the right of it, to the left of it, and so on. Okay, so the curl to get the H from A to H is actually quite simple, and we get these two terms from that H. So H points in the phi direction, and one of those terms went as 1 over r, the other term went as 1 over r squared. In general, both of those are equally important. If you're very, very close in to the origin, very close to the dipole, everything is inductive. If you're very far from the dipole, everything is radiative. Okay? So that gives you an idea of these vocabulary terms, induction and radiation. Induction are fields that just hang around, orbit around the dipole itself. Radiation is the transfer of power away from the dipole, presumably towards another antenna that's going to catch it. Okay, so we have these two terms, and it's instructive to say, okay, well, where's the crossing point? Here's the line for 1 over r squared. Here's the line for 1 over r. Where's the crossing point? And we looked at a critical. We set these guys to equal to 0. We looked at the critical distance, and that one is k, 2 pi over lambda. I'm sorry, lambda over 2 pi. Roughly a sixth of a wavelength. So if I'm at a gigahertz, a foot of a wavelength, 2 inches away from the antenna, I'm in the far field. I'm in the radiative term. Okay, so very, very, very close. So I think it's quite beautiful that the wavelength, the unit of measure for the particular wave, falls in naturally into this separation between the induction and the radiative. Okay, and so that's a very nice rule of thumb to kind of keep in mind. If you're out at least several wavelengths out, you neglect induction. If you're within a wavelength, it's all induction. Okay, and that should tie back into your undergraduate statics and low frequency quasi-statics, electromagnetics, where you've got two curls, do loops close to each other, and there's an inductive field between the two. Well, those are fields that you're sucking ordinarily those fields would not radiate, they just orbit around, and you're sucking that energy into a whole other lead inductively. So inductive coupling in a transformer, for example, or inductively in an old-fashioned metal detector, where you walk through. Those are made with big loops of wires in their frame, and they set up a magnetic field, and as you walk through there, you disturb that magnetic field. You disturb the mutual inductance between those loops, and you measure the back EMF of that. Okay, if you're carrying metal objects like an artificial hip or something like that. Okay. In our roadmap, of course, we go J to A to H to E to S. Everything is a curl. An integral followed by curl cross product. So the curl of H gives me the electric field. It's kind of nice that I have already assumed a definite cosine term in time, so this integration in time is quite easy. And I didn't do out all this curl. I know you rushed right home and over the weekend did all those terms. And it turns out a little bit more complicated. Remember, the magnetic field was pointed in the phi direction. That's the direction in the azimuthal. Turns out that E is perpendicular to that because of the curl relationship. And there's a component of E that points in the theta direction. There's a component of E that points in the R direction, away from the dipole. Okay? It should be no surprise that there's a 1 over R squared and a 1 over R cubed in the E field that points out in the R direction. So those are purely radiated, purely inductive terms. And then for the theta term, I've got 2 inductive terms and I've got one radiative term. So after all of this, I have 2 terms that are radiative, and everything else is electromagnetic waves or fields that just orbit around. They're very, very busy, they're oscillating, they're moving, but they go nowhere at all. I always think of them like a merry-go-round. And it's that one kid in 100 that flies off the horse and goes off into the... Bad analogy. Sorry. All right. Never mind. I'm sure there's... Come up with a better, cleaner analogy. I'll subscribe to that. If you take E cross H, you get a whole string of terms. We get an S in the theta direction, and that's a pointing vector that moves around. Let's see, if I remember right, that's from the North Pole to the South Pole, right? So we have the S that orbits. That's S sub theta that orbits around my dipole, and then we have an S sub R. And that's, if we think in terms of I hate to be biased, but I like radiative. This is an antennas section of the course. Antennas, we generally think in terms of getting energy from one point in space to another. So that's our hero, or potentially our hero, is the pointing vector that moves away. And of course, that comes out of the H term, which is in phi, and the E that's at the theta. So I have E, theta, H, phi, cross product giving me an S in the R direction. If I time average all these terms, all of these terms, here's a twice omega t, here's another twice omega t, here's another twice omega t. Those terms spend half the time above the axis, half the time below the axis. They time average out to 0. So those, again, are very, very, very busy fields, but don't go anywhere. They're just bouncing up and down at twice omega. In the R direction, things aren't much better. Twice omega, twice omega, twice omega, twice omega. If I time average, that's what these brackets mean. If I time average, those all average out to 0. The only term that's left is this one paltry little 1. So the time average pointing vector, the power flow away from my dipole antenna is this one simple term. That's all there is. Did you go back and did you guys go back and plot the sine squared of theta? Did anyone do that? No. How about anyone go in on my website and looked at the lovely plots that one of my TAs did a number of years back?
Polarization.
Pardon?
Talk about polarization.
Well, just what this S squared is, this sine squared theta, what this shape function is. Oh, take a look at this, right? There's a frequency term in there. There's the strength of the current. There's the length of the dipole here. There's a 32 pi squared there. There's a speed of light. There's a material constant there. There's really only two geometric factors. There's the 1 over r squared, which we recognize from the far field treatment. Right? That's the same 1 over r squared power flow, power loss, the 1 over r squared law. As I get further away, that's my peanut butter analogy on a basketball, remember? Right? No one remembers. If it's not that doesn't stick. The peanut butter doesn't stick to anything, right? All right. The sine squared is the only interesting shape parameter of that. Right? So the question is, what the heck does the sine squared theta look like? And it's plotted really nicely on my website, and it's not that hard to draw in MATLAB. But the short answer, and coming from my first name, is this is a donut, right? This looks like a donut in theta. So if I think in terms of what my theta is lined up with the axis, okay? And if I'm standing looking down on this antenna, I don't see it. The antenna has a length dl, but I don't see it. I see just the spike of a delta function. So if I'm right north of this thing, theta is equal to 0, sine of theta is equal to 0, sine squared of theta is equal to, sine squared of 0 is equal to 0. I'm getting no power flow if I'm completely on north of that thing. Right? If I'm on axis, pi over 2, sine is maximum. It's 1. 1 times 1 is 1. And so at that level, I'm seeing all of it. I'm seeing contributions from the entire, perpendicular to the entire antenna. So that's where my signal is strongest. So I go from 0 to a maximum, and then I start decaying back down, back to 0 again, looking at it from the bottom. So really what this sine squared theta is it's the projection. It's a simple geometric projection. And I get one sine theta from the E field, and I get the other sine theta from the H field. And that's where those guys are coming from. So it's a very simple thing. Now it's actually kind of interesting. If I have two dipole antennas talking to each other, and I'm exactly lined up broadside, then I'll get a maximum coupling, radiative coupling. As soon as I detune one, I lose an angle, which I can get back if I tilt one relative to the other. So if I'm transmitting and receiving, then I actually get the sine to the fourth. And actually, because of the projection, it turns into a cosine to the fourth dependence. So there's this Lambert's law that's of radiative transfer that goes as cosine to the fourth coupling, and it's just really nothing more fancy than this small misalignments in position and tilting, okay, which comes from shape factors like that. Okay. So think a little bit about that sine squared. Oh, and then notice as we started this whole thing, there's no change as I walk around the antenna at any particular thetas. Okay. So as I move away from it, I lose my power as 1 over r squared. Nothing happens. It's all symmetric in the phi direction. And as I move around in theta, I see no projection, a little bit more projection, a little bit more projection, a little bit more projection, a lot of projection, and then I start to decay back around. So I get lobes that look like this, swept around in phi. That looks to me very much like a donut. Okay? So, all right, that's where that's coming from. All right, now we can learn a little bit more about this We can learn a little bit more from this equation if we look at the total power. The units of this S, time averaged, is watts per meter squared. Okay, so what I want to do is I want to understand how much total power gets radiatively coupled off of this. So what I'll do is I'll pick a surface. So the way I imagine this is I have this donut sitting in space with this antenna pattern of the donut, and I throw a net over the whole thing. And I say how much, what's the flux of power as it crosses this net. Okay, so I'm integrating across an entire surface, and it's then this dA. And it's kind of, you've done a lot of these integrations, and if you're like me, you've forgotten how to write dA and all the different coordinate systems. If you think it through, the incremental differential area of an area of a basketball, there's a RDR, but I can integrate that out. So I have a 2 pi times r squared, and then I have a projection sine theta d theta. Okay, so dA can be written in terms of 2 pi r squared. That's because I'm going to walk all the way around the area in phi, and then I have a sine theta d theta that I have to pay attention to because my S has this one term in theta. Notice the r squared in the numerator. That's kind of interesting, right? So let me go ahead and write the integration, and we'll see what happens to that. The integral 2 pi omega squared I squared dl squared. There's my sine squared theta over r squared. And then the other constants are just 32 pi squared c cubed epsilon. And then I put in my r squared. That's this guy here. I put in a sine theta d theta. Okay? And the r squareds cancel. Okay? And that, at first glance, you have to sort of think about that and say, well, why did that happen? Well, if I've got this dipole and I move some distance into the radiative field, right, lambda over 6 away and further, and I drop a net over this, that net is going to catch all the amount of power that radiates out. If I make that net a little bit bigger or a little bit smaller, doesn't matter. I'll still capture all that peanut butter. I'll still capture all that power. Okay, so the fact that I'm integrating across a closed surface means I'm going to scrape off all the peanut butter from the basketball or the beach ball, depending on, regardless of how thick it is. I'm going to scrape it all off and collect it onto a piece of rye bread. Okay, all right. So this stuff here is all constant with respect to the integration. So it's an I squared dl squared omega squared over 16 pi c cubed epsilon, and then I'm integrating. And I love these dipole antenna. I love these antenna problems because you always get these really fun integrals that you don't always see, but they look pretty and they're really nice. In this case, I get a sine squared and another sine. I happen to get a sine cubed, and that gives me a 4/3. So I get 4/3, and so I get an I squared dl squared omega squared over 12 pi c cubed epsilon . And the units of this, S was watts per meter. I'm integrating across an area, so this is watts. And if I look at this, I've got a term that goes as I squared. And then I have a bunch of other stuff. right? And if I just think in terms of units, power is equal to I squared times the resistance, right? So whatever this means, all this other stuff has to have units of resistance. So the power is equal to I squared times some R effective. And this R effective is equal to dL squared, omega squared, over 12 pi c cubed epsilon. And it's important to kind of note that I've got c in the denominator, and that's a big, big number, right? That's 3 times 10 to the 8. Epsilon's a small number, 10 to the minus 12, right? And then I've got an omega squared in my numerator. So if omega is big enough, I get a little bit of a benefit there. Okay, so I've got a big number and some small numbers and maybe potentially a big number. And if I'm sloppy about the 12 and things of that nature and the epsilons and the c's, I get something on the order of 80 pi squared. Okay, and then I get this ratio of dl squared, and lo and behold, it's related to a lambda, which is really pretty. So the R effective goes as 80 pi squared dl over lambda. It's quantity squared. Okay. So if I keep, okay, all right. So a few more things to talk about, right? So the strength of the current, the more current I have, the more current I drive through the system, quadratically, the more power gets out and towards the other antenna. So that makes some sense, right? So the I squared as well is, and then the R, this effective resistance, becomes our design parameter. So how do we make this couple better or worse, depending on what we want to have happen? If we have a high frequency lead on a circuit board or in a chip, and we're running at a very, very, very high rep rate, it's going to radiate. Maybe we don't want that. Maybe we want to keep all the energy on our strip line going from one circuit element to another circuit element. And then this radiation power becomes a loss term, just sucking the signal information out away from that lead, which is bad, and probably picked up on adjacent leads as crosstalk, which is worse, right? So you lose signal, and on the adjacent channel you get noise. So in that situation, you don't want any radiation. And so what can you do about it? Well, you've got a geometric constant, you've got the size of the antenna, and you've got the wavelength. If you do want to couple from dipole to dipole, again, there's not much you can do about the 80 pi squared, but you have a DL and you have a lambda. So that the very, very limited palette of engineering parameters here to work with in this very, very simple experiment. But it seems to me that if I've got an impedance of the antenna, and I'm thinking about radiation, then I also have that impedance of free space, right? And so there's a power transfer from one type of circuit element, the antenna, as an effective resistance, into the impedance of free space. So at some level, I'm going to have, what's the impedance of free space? 377 ohms. At some issue, I'm going to have 377 ohms. If I do 80 pi squared, pi is 3.3 and some change. 3 squared is 9. 9 times 80, 9 and some change times 80, 800, or if we are careful, which I'm not sure it's worth being careful, we get somewhere around 789.6 for that. I think that's probably a little bit overkill. And then I've got this dl over lambda squared. And so if I want to maximize my power transfer, then I want this guy here to bring the 789.6 down to 377. So for max power transfer, I have dl over lambda, and you should check my math, but I got it to be about 0.691. Okay, and so at that dl over lambda, I have maximum power transfer from my antenna to free space. Is there a problem in that statement? A contradiction in that statement? You're nodding.
The original assumption was the DL is small.
Right. Not a dipole. So it's not governed. This length antenna is not governed by the theory. So the basic thing is to flip it around and say, what did I say about a DL? It should be about an order of magnitude less than the wavelength. So DL must be much less than a wavelength. DL on the approximately equal to 0.1 must be less than or on the order of 0.1. If I put that in there, then I have 377 is equal to 789.6. And 0.1 squared is 1 over 100. So 377 ohms, it's not an equality. I'm just comparing the two. What did I say, 100? 2 over, so that's 7.9 ohms. So I've got 377 ohms loaded by a 7.9. What's my power transfer going to be? Tiny. It's not very efficient at all. So that's really the lesson here. Even as long as I can make this, which is 1/10, and remember I was saying it should be smaller than that. So instead of 1 over 100, it's 1 over 1,000, 1 over 10,000. What that means is dipole radiation is very inefficient. Okay? So that's the moral of the story. Now, what happens is there's a lot of them. There's a lot of dipole antennas out there. And so in their sheer numbers, they lead to things that are very, very consequential. And one of the things that they lead to is we'll go back to this. We'll go back to this. These equations here. If you remember, the interaction of light with matter is largely governed by dipole radiation. So if you look out in the sky during the daytime, what you see is light coming in from the sun, and that light has a lot of wavelengths associated with it. And we can see a small fraction of those wavelengths with our eye. We can see from blue up to red. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv for the rainbow colors. And so we can sort of see that range. And what will happen is the wavelengths will interact with a dipole antenna that's the molecule, a pollutant or some sort of molecule sitting in the atmosphere, water, nitrogen, whatever, and then it'll re-radiate back out. So there's a coupling in, which goes as 1 over lambda squared, and there's a coupling out that goes as 1 over lambda squared. So I'll have the general scatter off these molecules, to be 1 over lambda to the 4th power. So the shorter wavelengths get scattered much more than the larger wavelengths. The shorter wavelengths are closer to the size of the molecule, and therefore there's an enhanced response because of the the closeness of the two lengths. And because of the two-step process, it goes as 1 over the lambda to the fourth. So one common application of this is that the sky is blue because of the 1 over lambda squared times 1 over lambda squared is equal to 1 over lambda to the fourth interaction of Rayleigh scattering off dipoles. Okay? And that's the classical electromagnetic answer that you'll want to give your 3-year-old child when he or she asks you, Daddy, or Mommy, why is the sky blue? Right? Now, I am a stellar parent, and I knew that my 3-4-year-old would not understand Rayleigh scattering. Even though I used to read to my kids a book of my favorite equations, which I wrote myself, including wave equations and so on and so forth. I didn't quite get to this point. So I had to come up with a better answer than why is the sky blue? Okay? And here's how I decided I would explain it to someone who didn't sit through. How many lectures have we been together for an entire semester? By the time I finally can show you guys why the sky is blue? So it must be a much more simple explanation. And the answer is, these molecules, these atoms in the sky, are fairly simple materials, right? Fairly simple materials. So they are linear in their response, and they don't change in their response. And so in that nature, the sky, our atmosphere, acts as a filter. Okay? So the input, as I said, are all the colors of the rainbow. And so all those frequencies come into this filter, and some pass through, and some are rejected by the filter. And because I've got this, because these are small molecules with electrons on them, the electrons are what's moving up and down. They're moving along the backbone of this molecule in the atmosphere. So physically, what's going on is an electron moving. And remember, electron has mass, so there's always an inertia. And any mechanical system that has inertia, if I shake it slowly, it follows it brilliantly. If I shake it really fast, it can't keep up because of the finite speed that the electron with mass can move. So this is nothing. So this is nothing more than a low pass filter. So the red light goes through the system. The bluer light gets scattered off or rejected by this low pass filter. Okay. So we could explain why the sky is blue without any electromagnetics, which I think sets you up much better to answer the question from your 4-year-old or 3-year-old. Why is the sky blue? Right? Okay. So those are two explanations, and they're really one and the same. They're really one and the same explanations. One is the Rayleigh scattering, the 1 over lambda to the fourth, is the electromagnetics is sort of what a physicist would think about. In our jargon, in our world of electrical engineering, we tend to look around and we always see filters, and so once again we have a nice filter response, and it's very natural. Now, my hand waving would not have gotten the power to the fourth power, but it's we could probably, in hindsight, come up with some rationale for that as well. Have a number of poles in our filter system. I feel less happy arguing that without knowing the answer, but there it is. Okay? All right. So, what if we wanted to do better? Well, we know that we can't pull the length all the way up to 0.7, 70% of a wavelength. We know and keep the same analysis. But it does point us to the fact that, thinking about the sky blue, thinking about the interactions, it does suggest that we want an antenna that has a length that's longer, or at least closer to the length of the wavelength that we're transmitting on. And so we want maybe we can think about it as a better resonance between the length of DL and the lambda of the wavelength that we're working at. So we don't know what the answer is, but we have a direction of what we might want to model. And so let's start all over again. But let's start over again with a current distribution that's much longer. Okay, so we'll go right back to step one, and we won't model a dipole antenna anymore. What we'll do is we'll model an antenna of height h, and there's two geometries. They're both equivalent. This is a center fed with an antenna going up and an antenna going down. And both of these I'll make symmetric in H. Okay. I could also do the same thing I have an antenna sticking up of length h, and then I can put a mirror, okay, on the ground. And remember, if I stand in front of a mirror, or if you stand in front of a mirror in the morning, you see a reflection of yourself, right? And so one way to think about that reflection is that there is there's a virtual image that's reflected off of that mirror. Okay. So one thing you could do, these are two equivalent geometries. It's just a question of how you want to build it. And this, if your wavelength's really long, then you've got two very, very long pieces of metal. And it saves a lot of headache to cut it in half. And so you have this. But then you have to figure out how to make a mirror. And that mirror has to be a metal surface. Well, if your wavelength is big enough, that metal surface can have a lot of defects in it. And so if you're a gigahertz or shorter, a foot, 2 feet, 100 feet, well, that mirror can be like a hurricane fence. You know, so you can just throw a wire mesh, a really sloppy, easy to make, hurricane fence under the bottom of your antenna, and at the wavelength that you have, it's a beautiful reflector. Okay? Or if your antenna is small enough, then you can polish your silicon and coat it with metal and do things of that nature to create an image charge as well. And then the advantage is you only have to make one very, very precision arm of that. Okay? So both of these are the same, give you basically the same antenna problem. Now, we will I'll label this as z equals 0, and this axis is my z-axis. So up to a certain point on my antenna will be a length z, and I'm going to take a dz element. So what I'm going to do is I'm going to write what is my current distribution at some arbitrary position z, and then I'm going to add up a bunch of dz's till I have the overall distribution. And I've got to kind of do something to figure out what my current distribution is. But it seems to me that if I make this less than a wavelength, or less than half a wavelength, if I make h less than half a wavelength, then I'll have some current that goes up to the end of this antenna, and it'll turn back around, and it'll come right back into the feed. Okay? So I'll have some sort of standing wave pattern for my current that's set up along this, that's set up on this thing. And then as I sweep through e to the I omega t, this current distribution will breathe in and out in time. Okay, and if I get my h just right, then that distribution will be sinusoidal, starting at 0 and ending at 0. Okay? If I don't get that distribution just right, okay, then what I might as well do is I might as well just model it as a sinusoid with a variational principle, by the variational principles, and just fit whatever the real curve is to a sinusoid. Okay? I'm doing analytic math. So whatever that distribution is I'm going to model as a sinusoid. So I am sine of beta h minus z times that. And then my bottom branch here will be I am sine of beta h plus z. And this will be for z greater than 0, and this will be for z less than 0. And so Im will be the maximum value of the current right about here. And this tells me basically what we are. Now, again, if I pick h just perfectly, then it will be a nice sinusoid. If I don't pick h perfectly, then it'll have a distribution that I will approximate as sinusoid. And there's a whole nice technique, I don't know if you've run across it, where you can optimize the fit between whatever that distribution is and the assumed curve. That if it's Fourier series, it's a Fourier series if we do the sinusoid, or in general if it's a variational principle. Okay? So, however you want to look at this problem, those are ways of thinking about it. Okay? And again, I'll have the same current distribution there, and the virtual image down below there. And let's add in my geometry here. I'll have the capital R will also be the same as little r. I'll put my origin right here. And so my little r will be the same as my capital R. Oh, I'm sorry, my little r will be out here to some observation point. This angle here is theta. If I'm at some z away, then this is my capital R. And notice that there's a projection here, just like the far field. And I'll write it down here. This capital R is equal to R minus Z projected onto this line here, cosine theta. So this little lip here is Z cosine theta. Any questions? Okay. So, again, our first job is to come up with the A. And I've lined up my antennas in the z-axis. So my current distribution is going to be in the z-axis, which means my A will also point in the z direction. So A will equal AZ because it will follow the current. Okay? And then to get this, we have to integrate all the little dAs. And we have the Green's function, e to the I beta r over r, the strength, the 4 pi, and the mu. And so the integral for AZ So this is from the bottom branch, minus h to 0, and this is the top branch of the antenna, 0 to h. Now, depending on your patience and my patience, we'll do both the far field and the near field. But let's begin by just the near field. Okay? I'm sorry, just the far field. Okay? So in the far field, we can decouple the R dependence from the theta and phi dependence. Okay? So in the far field, in the bottom field, when I substitute in r minus z cosine theta into the denominator, the r z cosine theta doesn't matter. So I can just pull the r out through the denominator. So r is approximately equal to r in the denominator. I can't do that in the exponent. So this capital R in the exponent will be r minus z cosine theta. And we now see that z cosine theta, this little guy here, as this moves up, that phase term, that z cosine theta differential, grows. Okay? And so that phase term, how much the relative phase is here versus here versus here versus here, will matter. So there'll be a certain amount of there'll be something moving from this dz, and in the far field it'll be the coherent superposition from this guy, this guy, this guy, this guy, this guy, and whether or not those waves add up in phase, out of phase, or somewhere in between is everything to do with the z cosine theta term. So in the exponent, in the complex exponent, here, that phase term is critical. In the denominator, not so much. Right? So another example of the application of our far field to the problem. And our A sub z is mu im e to the minus I beta r over 4 pi r. There's my r dependence, the propagation part of it. And remember what went on, the rest of it was a function of theta and phi. Right? And so when we did the far field work, we had this guy here, and then we had the gain, the antenna gain. Be a little sloppy with that terminology, but it's the shape function of the antenna, the positioning of the antenna. Well, we're not being general. We are actually we're actually pretending that we're going to be able to do this at these integrals. So there's our general expression. And really this is not horribly difficult. I can rewrite the sign as complex exponents, lump everything together and hack out an answer, solving it at 0 to nh. Okay, you should be able to imagine yourself doing this, or you can, or I believe there's actually even this is actually even commonly listed on an integral table, so you could just get at it that way. It's not horrible, is what I'm getting at. A few little tricks in there, but not terrible. But what I'll do is I'll do a special case, and I'll say h is equal to lambda over 4. There's two h's in my antenna, right? So this is a half wave antenna. Okay, and that's it's popular. It's a popular situation. So if I look at these guys here, the sign's there. The beta and the z being a lambda over 4, beta is 2 pi over lambda, and z is lambda over 4. I think that gives me a 90-degree phase shift. So that becomes a cosine term. And the sine of beta h minus z is equal to the sine of pi over 2 minus beta z, and again that's equal to the cosine of beta z. Okay? So we're making our life a little bit easier, cleaner. So if I lump my two integrals together, I can now bring my two integrals together, and my complex exponents cooperate with me to give me a cosine term. And so now I can use a trig identity, the beta z and the beta z cosine theta, the projected beta z. So and now I almost have a reasonably easy integral to do. And remember, beta is 2 pi over lambda. So z at lambda over 4 gives you something really nice here. And if you substitute all this in and simplify, I get something that's almost palatable. Okay? So I'm trying to give you a flavor for how these integrals for the f of theta and phi work out. Okay? And so you can see the role of theta is to provide you a phase shift for things. And we now have the same problem, or we now have the same step of the problem that we did with the dipole. Which was, we've got to make the projections, cosine theta and sine theta, we'll get an AR and an A theta. When we go ahead and we look at the symmetries, we still have all the z, the currents in the z direction. So as I walk around this, I still have perfect phi symmetry, right? I still have perfect phi symmetry. So as I walk around the wire I still see the same wire. I don't see any variation in that. So I really have very few curl equations to do. So all the lessons that we had before gives me a mu h phi in terms of the del Az del R. So we're in the far field. We've got really nice symmetry in the phi direction. Once we did this crummy integral, just to review, everything we've done has been about getting this integral in the right shape, right? That was the thing we fudged over in the far field for the f. Remember I said let's assume we can do this integral. And then for the delta function for the dipole, that integral was cake because it was a sifting property. And so we had to sweat a little bit to get to the form for the far field that we had before. Okay? And so this is my f of theta and phi from what we had before. But once we have that, for at least for this problem, we're just doing curls. And the leading term will just be 1 over r. And in the far field, E will be perpendicular, so it's going to point in the theta direction. Again, there'll be terms of 1 over r squared, 1 over r cubed, and so on. But we're only in the far field. And so we can write down E sub theta. And again, what I'm doing is I'm drawing from the symmetry of the dipole and the rules we established for the far field 2 lectures ago. So if you go back through all that, you'll see that this is consistent with the shape factor in there. Okay? And finally, the S is going to be 1 over r squared. And that's where we'll quit for tonight. Okay? We still have a few more things to do on this. I want to look at the power and so on, but that's where we got. So very, very cumbersome derivation to get us to the proper A. But once we do that, the curls go pretty quickly, especially if we learn from the work we did before for the far field and from the dipole.